The next presentation is developed by William DeRoset and Peter Lagasse. Peter Lagasse probably doesn't need a lot of introduction around here, but he's a senior hydraulic engineer with Ayers Associates. Since 1995, he's served as a principal investigator or co-principal investigator for 8 national cooperative highway research program projects on a wide variety of bridge scour and stream stability projects. Most recently, he was PI for a project to investigate improvements to the existing contraction scour analysis procedures. William DeRoset is a senior hydraulic engineer with Ayers Associates and co-author of the 24-47 contraction scour study. His primary contribution to the effort was in the risk and reliability evaluation to support quantitative conclusions concerning the improvements to contraction scour elevation methods developed by the study. So I will go ahead and introduce you to the stage.
Okay, everybody hear me okay? Yes, I have amplification. Okay, let's shift over to the other preview here. All right, I am being outsmarted. There it is. Come on up. There we are. And because this is not a PC, we're going to pick on poor old Macintosh. There we are. Okay. So this is our final presentation on the NCHRP Project 2447, NCHRP Report 971, and where we looked at revised clear water and live bed contraction scour analysis. So actually, let me give you all a little bit of background before we move on into that. So this was actually occasioned by a prior NCHRP report, NCHRP Project 2434, when we looked at risk and reliability of the existing scour prediction technology. And what we found was for pure scour, there were reasonably good data sets available. We could evaluate the both the accuracy and the uncertainty associated with the pure scour equations, and similarly with the abutment scour equations. We had relatively good data sets when we could evaluate basically the risk and reliability, the reliability of those. So how variable your results are for a given prediction. And when we reviewed contraction scour, what we found was the data sets were lacking. There were no accurate field data sets that would allow us to evaluate the reliability of that. And also, the abutment scour and pure scour relationships were design equations. So they had a certain amount of conservatism baked into them, and we were able to quantify that. So what the bias of the equations were. However, with contraction scour, the existing technology is based on flow and sediment continuity, and was fundamentally derived from first principles. Those are true prediction equations, and they have no conservative bias built into them. And because there is a fair range of uncertainty, unknown but large range of uncertainty associated with the contraction scour equations, we wanted to investigate that further. And NCHRP agreed with us, or rather agreed with the engineering community, and we ended up putting together this NCHRP project. So research team included my colleague Peter Lagasse, who was our principal investigator, Dr. Rob Edema, who was the co-PI. His team performed all of the flume evaluations, and as we'll see, we had a couple of excellent graduate students helping us out. Myself, Mr. Scott Zai, formerly of Ayers, now living his passion project at the U.S. Forest Service. Mr. Paul Klopper, He was with us and retired, went through the revolving door, and now works with Catalina Civil. Ali Narazapur, and he was a PhD candidate. He has since graduated and moved into industry, along with Ali Fakhri. We had a double Ali team. So there. And Narazapur did the primary work on the sediment transport and looking at the contraction scour relationships. And Mr. Fakhri actually developed the vena contracta data that we use to modify those equations, as you'll see. So, project schedule, this was performed between 2016 and 2020, which is why we presented a preliminary version of this at NHEC 2020. This is our final stab at this. So, and the document NCHRP Report 971, which documents this effort, was published in November. So now, what were we trying to do? We wanted to develop live bed and clear water contraction scour equations that are suitable for risk-based design. We wanted to be able to quantify the bias and uncertainty of these and set them in such a way that they would be reasonable for design purposes. And then we wanted to encompass a wide range of hydraulic conditions, including varying contraction ratios. And as you'll see when we talk about what we would like to do someday in the future, we also wanted to look at different entrance conditions, so different abutment shapes, and also move away from the long contraction concept to a short contraction. We'll talk about that in a minute. So we used a single non-cohesive sediment size in the interest of, frankly, resources. We did not have the resources to do a variety of sediment sizes. So in the 8-foot laboratory flume at Colorado State University. So we developed a contraction scour data set. We have 19 well-developed simulations, and we will talk about that in a little bit. I see that as a major contribution because it was well instrumented and well documented. And so those data sets are available to do extensions of the research that got started here. So a couple of things we needed to do. We had to do a literature review and fundamental hydraulic analysis. So what are the variables involved? What do we want to vary to see what's going on? And look at the existing contraction scour data. So how does that perform? Where are the gaps? What gaps do we need to fill? Develop and execute the laboratory test plan. Apply computational techniques. This was very limited in this research, but is a wonderful avenue for further study. Develop enhanced clear water and live bed contraction scour equations. So we looked at the equations. We saw an opportunity to improve them or capture more of the physics of the system into a relatively easy to apply equation. And then finally, we developed both a NCHRP report and a training manual for application of these. And then we got to submit the report, review it, and get it published. So this is just a review of the hydraulics of a short contraction. Most bridges are short, hydraulically short contractions. So as you can see, we have flow, make sure that's working, flow moving in here. We have an uncontracted width. We have a contraction, a relatively short contraction. And we can look at the flow profiles as we move through this along the center line. And you will notice that in the laboratory environment, we started off with a normal depth, starting water surface elevation, so we did not see a whole lot of variability in there until we got into our contracted section. And then as we move upstream, we have backwater associated with the bridge, and eventually, someday, if this went far enough, we would have a theoretical upstream normal depth as well. Some of the research that did not pan out so well was actually looking in detail at this theoretical upstream normal depth. So we did do, for flow visualization, we wanted to see what the contraction patterns are like in our opening here. So if we look at the throat of that bridge opening as we move into the contracted section, there's a lot of things going on here. Now, I don't have moving graphics. There are no robots involved, so this will all be quite static. But you can see that the flow, as we move around that obstruction, we have turbulent structures that are forming, and as we saw in our excellent prior presentation, Dr. Lai showed those turbulent structures forming at the corner of our opening. Here we have a more gradual opening as opposed to that sharp vertical wall, but we still have turbulent structures forming there, and in addition to the flow contraction, those are all interacting simultaneously, and if we have enough constriction, those two turbulent structures that form as we force water around the abutments will actually interact in the main channel. That is not what we are studying. Those are local scour phenomena. We're still fundamentally looking at that sediment continuity through the bridge opening. So we moved on to looking at our flume design. This is a 4-to-1 contraction ratio, and we looked at several different ones, as we'll see. And that's Rob actually admiring one of his Clearwater contraction scour runs. So we had flow, let's see here. So traditionally, we had no good measurements of depth of flow. Incorrect assumptions on the depths of flow, so we either did not get good information or the researchers were making poor assumptions about what those depths of flow were. Most studies were done under Clearwater conditions. This study was performed under both Clearwater and live bed with sediment supply conditions. And the field data sets were just flat not usable. So that was the existing state of practice. So we wanted to adapt that. This is one of the better studies that we had as part of our literature search. Check my time. I'll talk endlessly on this if you let me. So here we have a water surface. You notice they already started 22 minutes in. It takes a little while to rev up your flume and start taking measurements. And if you're working in a sand or gravel bed environment, you're already going to be moving that sediment in the contracted region. So by the time you get to that 22 minutes or so, you've already developed a pretty well-established scour hole. You can see it's evolving through time here. You'll also notice that the distance here, this is about a 30-foot flume. So what, by the way, what was the flow depth before scour? We don't know. And one of the things about the state of practice, the way we apply contraction scour today, what do we apply at our contracted section when we evaluate scour using the Heck 18 equation? We're looking at the pre-scour flow depth in that location. So if we want an equation that would improve on that, we would actually want to make sure that when we evaluate the scour depth based on that pre-scour flow depth, that we're getting accurate estimates. And we just don't know. Our current scour technology compares depths, fundamentally. We have a pre-scour depth and a post-scour depth, or rather an upstream flow depth at equilibrium and a contracted scour depth at equilibrium. That is the data that we have from our existing studies. So to remedy that, this was the lab setup. So this is a 160-foot long flume. So the area of maximum interest is actually in this short contraction reach where we had all of those flow field features, the turbulent structures that are formed at the corner of the abutments, and what we describe as a vena contracta here in a minute, interacting. So that's our area of maximum interest. And then we extended the flume well downstream. So there's the 8-foot flume before we installed, or rather before CSU installed the experiments. So as part of the measurement and instrumentation, they took water surface profiles as a function of time. They were also looking at point velocity measurements. They also did large-scale particle velocimetry, so they were dropping lots of confetti in the water and getting video capture of that as they looked at the surface. And then the time variation of the bed elevation along 3 transects in the water column. Also, one thing that is easier for, you saw yesterday, Cornell presented his ESTD, and there they were actually doing real-time laser scanning, which is really easy to do in clear water, much harder in a live bed environment. So here they were actually taking point measurements along those. So we got equilibrium bathymetry. So once the lab team determined that they had reached equilibrium or something approaching equilibrium, they actually drained the flume and took a LiDAR data set of each one of their simulations. And then finally, we did some flow field visualization. So we looked at 3 different contraction ratios: 4-to-1 contraction, so 25% opening; moderate, 50%, so 2-to-1 contraction; and then mild, 3/4 to 1, so 1/2 to 1 contraction. So we also looked at, we originally were planning to look at multiple transitions, and the world is a finite place, so we ended up doing wing walls, so 45-degree transitions. So here's Rob continuing to look quite satisfied with his Clearwater contraction scour simulation. A couple of things to note: this was a relatively mild simulation, but you do see the 2 lobes of that local scour input. And then also, it's a little harder to see here, but there's actually a vena contracta reach where we see a little more contraction. So now, we can look at the time evolution of our water surface and bed profiles. And you can see through time, backwater decreases, the bed evolution changes through time here, and we reach an equilibrium scour depth. Now you notice this is varying through time. Those are those bed forms that are forming in that full long contraction. So typical LiDAR scan, you notice it's pretty noisy, and this was common. So here we just took a profile along the center line and also the wall, and 7-hour simulation in this particular case. We see that we got about foot and change of scour along the wall, rather less along the center line. Again, that is that local scour contribution, which we did not want to account for, because we use other methods to account for this amplification using the NCHRP 2420 method, the amplification from this contraction scour depth down to the local scour depth. So, water surface changes through time, and you can see that it doesn't change that much in the throat of our section, but you can see significant variation in the downstream water surface as that bed evolved and degraded into its equilibrium condition. Similarly, for this is a live bed example, and there it was actually a lot harder to catch to subtract out the influence of bed forms in the throat, and particularly downstream. So we had to account for that. One thing that we observed, and this was very much helped by the LSPIV data that we got, that particle image velocimetry, was that there was an additional contraction. So when we looked at the contraction, rather than this geometric width, the actual effective flow width was relatively narrower. And this varied with the unit discharge ratio, and then also, as we see, with the flow intensity or Froude number. So now, we look at this, and we wanted to evaluate where was the point of maximum contraction scour. We had to decide. We don't want to include the region that's highly influenced by local scour. We don't want to capture, we want to subtract out or average out the bed forms, because those are going to be time-varying features. And then finally, there was a region in which we consistently found, or the CSU team consistently found, a point of maximum contraction. And that was in this bridge opening, and it varied from 0.2 to about 0.6. If we grabbed more than this, we saw more results variability, less certainty, and if we grabbed less than that, we weren't necessarily capturing the region that was associated with that point of maximum scour. So with that, we were able to evaluate, well, look, we know what B2 is, so we know what this contracted width is, W2, in the HEC 18 formulation. We know what that is. That's easy to come up with. But this additional contraction associated with the vena contracta, we didn't have such good data for that. And it had a significant effect on our scour results. So took the lab data and took out the data for the very extreme constrictions where the local scour turbulent structures interacted with that center point, that vena contracta. And so we subtracted those off. We took the remaining lab data and we drew a line through it. And this line is very slightly different than what Mr. Fakhri developed for his work. It's non-dimensional. And so we developed a case of V. So this is the width ratio associated with that vena contracta versus the geometric width. And 5, good, okay. So now, got that, and the 0.5 and the minus 0.18 is empirical slush from our regression, but the rest was dimensional analysis and working through this data. So now, the result, how we apply this was to use that case of V factor, which remember is equal to or less than 1. Use this case of V factor to increase the scour depth. For the HEC 18 equations, you can just see that we have the unit discharge squared, the unit correction factor, d sub m, and all this to the 3/7, but we include that case of V in the unit discharge to account for that additional constriction or contraction. Similarly for the live bed equation, you have your discharge ratio, you have your width ratio, and that shows up in the W2. In general, this will increase your scour. Similarly, we also evaluated the NCHRP 2420, the simplified contraction scour equations that it uses, or that method used, to evaluate abutment scour. Recall that what we do with that is we have a contraction, and then we use an empirically determined amplification factor to account for the presence and the influence of those local vortices. So this is a simplified version. So Y2 for HEC 18, we simplify that a bit. You'll notice that they rearranged it a bit. This is geometric or algebraically identical, except that they have adjusted d sub m to d50. This is a slightly conservative simplification. Similarly, for the live bed equation, unit discharge ratio to the 6/7 and case of V. This will tend to increase our scour a bit. All that does is assume that this bed condition factor is equal to 6/7. So with that, when we looked at applying HEC 18 and the NCHRP 2420 method with these, it does tend to increase scour. And prior to doing this, notice that we are regressing Y2 versus Y2A. So we're looking at the post-scour flow depth, and I'll talk about why in a second. So, but we do get, it does increase the relative conservatism of the equation, which decreases the bias, which increases your effective factor of safety, it also increased your reliability factor, beta. So similarly for the NCHRP 2420 method, it is slightly more conservative equation, so we are over-predicting, but that is desirable if we want to have some degree of confidence, some reliability built into our equations. Now, we just applied K sub V linearly, and what you notice is, I'm not sure that's necessarily the ideal fit here, but that would be something that we could apply once we extend the data set and get more information, more data points here. So now, let's go to our conclusions here. So 2434, when we looked at reasonable reliability factors, and remember that a reliability factor is just how far away from your mean or your actual predicted value is the actual value likely to be. So how many standard deviations do you want to be conservative? Do you want it to be a prediction equation and half the time underpredict, half the time overpredict? Or for design, do you want to step and make sure that you are overpredicting, but you have some confidence that you are going to have a reasonable estimate? So what we found from NCHRP 2434 is that for reliability factors greater than 1.5, we needed scour factors where we just linearly increase the scour depth between 1 and 1.75 to 2.4. However, with K sub V, we can increase that statistical reliability. We can also reduce the variability. The adjusted HEC 18 and NCHRP 2420 equations, they agreed reasonably well. I think there's additional work to be done to refine that. And then the adjusted NCHRP 2420 contraction scour equation actually outperformed the HEC 18 equation for this data set. So less variability and was more conservative. So now, potential applications for this. Remember, this is just 19 data points. So we don't want to apply this willy-nilly. And the potential application here, well, uniformly graded, non-cohesive sediments. Didn't account for sand and gravel together, didn't look at cohesive soils. So width to depth ratios and entrance conditions comparable to the model studies. And that would be a relatively short, single span structure. For typical floodplain widths, we're looking at things that are less than 40 feet in length. And those are very commonly going to be hydraulically narrow. Now, this does have potential applicability to up to about a third of the bridges in the NBI as of 2020. So about 200,000 bridges. So for other bridges, we would not recommend using this K sub V factor because we just don't have the data for it. So we want to use existing best practice modeling practices, and then based on the results review, we would actually recommend the NCHRP 2420 simplified scour equations. So one other thing that we notice I talked about flow depths a lot and rather less about the net scour. That's because there's a datum issue with using that pre-scour flow depth. It decouples from the actual results of your prediction. And one thing that we found is if you use the downstream flow depth, which we called Y3 in the report, it might be a more reasonable candidate for evaluating the change in bed elevation from contraction scour rather than just these flow depths. So future work, refine and generalize the K sub V application, and in particular look at bridge pier influences, bridge skew, and that entrance condition. So if we have spill-through abutments, they are very likely to have different characteristics for that K sub V. And then finally, additional studies probably would be valuable, at least until we get into the next scour realm, where we're performing mobile bed hydraulics and directly calculating this, capturing the full physics or as much of the physics as we need to. While we're still using these prediction equations, we want to take a look at that contraction scour depth data. So if you're interested in this report, it has been published, and that's available at this Endless website URL. And with that, what questions do you have? Or do we have time for questions?
One or two questions.
Okay, yes. Yes. And I was in artillery for 4 years, so please speak up.
So you mentioned adjusting the NCHRP 2420 using the new contraction equations. So my question is that traditionally when you do a Scour analysis, there are equations in HEC 18 for each overbank versus the main channel contraction in Scour.
Yes.
And then you have the NCHRP, which is another contraction in Scour that applies to this basically same areas plus the abutment.
Yes.
The problem is that the criteria for deciding between live width versus clear water contraction in Scour between the two sets of equations are different. So you may end up with the clear water contraction in Scour calculated for each overbank and your main channel versus then you move on to calculating the NCHRP 2420 abutment contraction in Scour, you may end up with the live bed contraction in Scour. And then we've had, believe me, situations where we calculated contraction in Scour for leftover bank that was 15 feet, and then NCHRP 2420 gave us contraction in Scour of 10 feet for at the abutment. And our client is asking, how could the leftover bank contraction Scour be 15 feet, but the abutment would be less than that?
So
Now,
let
the
me.
question then is, are you able to overcome this double standard that exists in today's HEC 18 procedure application?
So the question is, so the way the NCHRP abutment scour equations are written in HEC 18 can lead you to that conclusion. However, if you're using scour condition A, so and this is totally off the topic of my conversation here. This goes into scour prediction a little bit for abutments. But if you're using scour condition A, you're looking at main channel hydraulics and evaluating whether or not it's clear water or live bed, and then applying scour condition A amplification factors. If it's scour condition B, where it's set well back and stable over the service life of the bridge, you would evaluate that using overbank hydraulic conditions, evaluate whether it's clear water or live bed. Typically it's clear water in humid regions anyway, and apply the scour condition B amplification factors. So there should not be a significant mismatch between clear water and live bed conditions for your calculations. And for anything more than that, I'm wandering way off into the weeds of HEC 18. We can talk offline. Are there any other questions, or is that it? Okay. All righty. Thank you all very much.